Hello, in homework 2, part 2C of the video, we're going to be implementing Broyden's method with step size adjustments and inversion of Jacobian as necessary when progress is slow. So basically, what Broyden's method is very similar to Newton's method, but it's a very less computational way of finding the root and k values. So basically, Newton's method for solving f of x is equal to 0. Use the Jacobian matrix J at every iteration. But the idea behind Broyden's method is to compute the whole Jacobian only at the first iteration and do one rank updates at other iterations. So what basically we're going to be doing is we're going to be updating the Jacobian based off the previous Jacobian. And we're going to prove this is true in this video. So what we need to do is we need to define a function called Broyden, because we're trying to solve it, and we want to take in a function of f. We want to take the first guess. We want to take the function of the Jacobian, and we want it to iterate 50 times with a tolerance of, you can see that this is very similar to what we did in the previous video for the Newton's method. So now what we wanted to do is we want to solve the Jacobian of the inverse, and we're going to do this by calling the linear algebra function, and we're going to be calculating the Jacobian at x of 0, which is the next guess. Actually, no, that's the first guess. x1 is the next guess. Okay, so it looks good. And we want to count. We want to do an inverse count. We want that to equal 1. And then we want the function of 0 to take in x of 0, which is the first guess. And then we want to iterate through this. So we did define that we wanted to iterate 50 times in this for loop. We want the change in the x minus the Jacobian, the inverse of the Jacobian. And we're going to do some matrix multiplication with the function of the first function. Now, we need to define what x1 is, our next guess. We're going to say that's the first guess plus the change in x. We can also say that what we want is the first value of the function to take in the next guess. And we're going to say alpha is equal to 1. And now we're going to want to iterate it through to find to update Jacobian based on the previous Jacobian. So we're going to see it whilst the first function is greater than first guess in the first function. So we're going to use the linear algebra to look through these values. And we're going to say that is less than the function of the first. So we're going to say when alpha, we're going to say it's equal to 0.75. And we're going to say, go back to alpha. Now we're going to need another for loop within this. So if alpha is less than what our tolerance is, we're going to say basically 1 to the minus 10. We're going to just make it a very small value. And then we want to find the Jacobian of the inverse of the function. And we're going to use that by finding, we're going to be using that by the inverse of this. And then we're going to need to also make sure we put the inverse count so it doesn't mess anything up into the code. And we want to step that up by 1. Okay, so the code is not quite done yet because we need to define what the change in x minus the Jacobian and the inverse of that, and we're going to do some matrix multiplication. We also need to define x1 but we're going to make sure this is outside of the function, outside of the for loop. X1 equals x0. I said out of for loop, I meant out of the, what is it called? If loop. So we're gonna also need to show what this is taken in. So we're gonna make another if loop. This one's a little different. This one's we're gonna see if n and p dot lin ouch norm, taking the first function. If we say that is less than the tolerance, it'll break it, and then it'll come out of that loop. So now we're gonna need to find the change in x. So say x1 minus x0. We're gonna need to change in the function f1 minus f0. We also need to say x0 is equal to its next guess is equal to its first guess. We'll also say the function of 0 is equal to the first function as well. Okay. Code is getting kind of confusing because it's so long, but we're almost there. So now we're gonna name this DEM, and we're gonna do some matrix multiplication by taking the transpose f underscore Jacobian, inverse of that, multiplied by df f underscore Jacobian. We take the inverse of that, and we see that the Jacobian of the inverse. Now we're just writing in the formula that we needed to write. Dx minus f underscore Jacobian inverse that df. Now over here in the bracket, we're doing some matrix multiplication, so we're gonna need another bracket. We're gonna take the dx transpose at f underscore jack underscore inverse divide by what we just specified. We're gonna print I plus 1 XO alpha, and then we're gonna return I think it goes right there, yeah. We're gonna return x1, the next guess, and the inverse count. it's loading. It's taking a while. Does it need to be? What the? Was it here? Oh, let's try it now. Oh. Yeah, that doesn't look right. I think I did say that was lowercase. Yeah. I didn't even realize I made. And you're gonna have a lot of code. There's gonna be a lot of mistakes. I just hope it runs. Alright, looks good. Let me run it all, because I'm gonna need to use this. So we're gonna make another function. We're gonna call it funJac equals jax.jacobian, and we're gonna use that fun function we made for Newton's method, and then we're gonna use that for Broyden's method. So we're gonna say f is equal to fun x0 is equal to j and p dot array. We're gonna make it an array. We're gonna need the brackets, and we need to make sure it's a floating point. And then we're gonna do that f Jacobian, the function, we're gonna call it into this Jacobian that we made. So what do we call it? Fun underscore jack.